Welcome to the deep dive. We're plunging right into some really groundbreaking developments today.
Absolutely. We're looking at AI, quantum computing, and robotics.
Yeah, and the pace is just dizzying, isn't it?
Yeah,
I mean, just looking at the headlines from, what, March to August this year?
right. 2025, it feels like the world is genuinely transforming right in front of us.
And you, our listeners, you've sent in this fantastic stack of articles, research papers.
A really interesting mix.
So our mission today is pretty clear. Cut through all that noise, pull out the really key bits of knowledge, you
To
know?
find those aha moments, that's the goal.
Exactly. The stuff that makes keeping up with all this genuinely exciting.
And we've got a lot to cover. I mean, from deep quantum physics breakthroughs to some tricky ethical questions around AI and robots that are getting incredibly sophisticated.
So we're connecting the dots, basically. Exploring the so what behind it all.
Precisely. What does it actually mean for you, for everyone?
Okay, let's kick off with quantum computing then. There's been this, constant stream of news. It really feels like that, yeah.
Like every week, there's some new impossible barrier that's suddenly not impossible anymore.
What's the big picture takeaway for you?
I think the biggest thing, honestly, is that we're shifting. We're moving past just demonstrating quantum concepts.
Right, the lab experiments.
Exactly. Towards building machines that are, genuinely practical.
Yeah.
And reliable.
Okay, practical and reliable. That sounds like the real game changer.
It is, and it's happening on two fronts. You've got these fundamental breakthroughs, like an error correction and stability, and then you also have very real, tangible engineering progress in the actual hardware, the materials.
So give us an example. What's something really exciting on that reliability front?
Well, okay, just last month, there was this research team. They managed to create a quantum logic gate, but using fewer qubits than you'd normally expect.
Fewer qubits. How?
They use this really clever encoding method. It's called the GKP error correction code. Bit technical, but basically. It uses continuous quantum variables, not just the usual discrete ones, to protect the information. Makes the qubits way more robust against noise and errors.
Okay.
And the really cool part, they did this by entangling quantum vibrations inside a single atom.
Whoa, inside a single atom.
Yeah.
That sounds like sci-fi.
It's pretty wild, yeah. And it builds directly on earlier work where teams were simulating these super complex, fault-tolerant codes that people thought were maybe impossible to implement.
So we're really cracking the code, literally, on making these things stable.
Exactly. Stability and resilience, that's key.
But you mentioned hardware, too. Are we seeing jumps there as well, not just the coding?
Oh, absolutely. It's not just software or error codes. We're seeing totally new materials being developed. For instance, very recently, researchers showed off a new quantum material that uses magnetism to field the delicate qubits from, environmental noise, heat, vibrations, all that stuff.
Magnetism. That's different from the usual cooling and shielding, right?
Completely different approach. And it points towards building quantum computers that are just inherently more stable from the ground up, much more robust physical foundations.
Okay, so connecting the dots then. Fewer qubits needed for logic, better error correction, more stable materials.
Right. Add in things like achieving an unconditional exponential speedup using clever error handling on IBM's chips.
Unconditional, meaning it works regardless.
Pretty much. And more efficient ways to create these crucial magic states needed for fault tolerance, plus new amplifiers that are 10 times more efficient and keep things cool.
And I saw something about a super thin chip replacing bulky optics.
Yeah, that Harvard Metasurface chip replaces hefty lenses and mirrors with a single nanostructured layer. It all points in the same direction,
Which is...
moving faster than maybe anyone expected from just quantum demos to genuinely quantum useful machines.
So, okay, why should we care? Stable qubits, magic states, magnetism, what's the real-world impact?
Look, these are the absolute building blocks. They let quantum computers get out of the niche labs and start chewing on problems that are just intractable for even the biggest supercomputers we have today.
Like what kind of problems?
Think about discovering new drugs, simulating how molecules actually interact with incredible precision. That could revolutionize medicine.
Yeah.
Or designing brand new materials from the atom up, materials with properties we can't even imagine yet, or tackling massive optimization problems, logistics, finance, supply chains.
Things that could save huge amounts of resources or energy.
Exactly. These stable, efficient qubits, they're basically paving the road to, well, maybe a whole new era of scientific and industrial breakthroughs.
Okay, wow. Let's shift gears from the quantum level to AI, the digital brains.
Right. Equally mind-bending stuff happening there.
Yeah, it feels like it's not just about making the models bigger anymore. It's about how they're learning to think. Or processing information, maybe.
Yeah, that's a great way to put it. And what's really fascinating, for me at least, is watching AI's understanding evolve, but also seeing its surprising blind spots pop up.
Tell me about the evolving understanding part first. What's the big news there?
Well, there was this really interesting discovery recently. Scientists figured out how neural networks seem to achieve understanding.
How?
Initially, they treat sentences almost like puzzles. They focus on the word order, the syntax.
Okay, structure first.
Right. But then, after they've seen enough data, something flips. There's this abrupt phase transition. The researchers compared it to water flashing into steam.
A sudden shift.
Exactly. And suddenly the network pivots. It starts diving into the actual meaning of the words, not just their order.
Whoa, that sounds significant, like moving beyond just pattern matching.
It suggests a potentially deeper kind of learning, yeah.
Yeah.
Getting closer perhaps to how we process language.
Okay, that's a huge leap. But you mentioned blind spots. Even with this deeper understanding, where are they still falling down?
Well, that's the paradox, isn't it? Even these incredibly powerful models like ChatGPT, they really struggle with nuance. Human context, common sense, ethical reasoning.
Ethics, how so?
There was a study just last month. Researchers took standard medical ethical dilemmas, tweaked them slightly, and found the AI often defaulted to answers that felt intuitive, maybe, but were actually ethically flawed. Basic errors, surprisingly.
And didn't I see something about them messing up with simple words like no or not?
You did. Another study earlier in the year, vision language models looking at medical images. Ask them a question with a negative, is there no fracture? And they often get it wrong.
That's critical in medicine.
Yeah.
You can't have that kind of error.
Absolutely not. It shows they lack that fundamental human grasp of context and meaning, especially negation. Precision matters, life or death sometimes.
So it's like you said, a paradox.
Yeah.
This emerging understanding on one hand.
Right.
But still these really basic, almost naive mistakes on the other.
Yeah.
Like a super smart savant. Brilliant calculations, but misses the obvious sometimes.
That's a good analogy. Brilliant in specific tasks, surprisingly vulnerable in areas that seem basic to us.
But despite these flaws, AI is being used for some amazing things, right? It's not all just theoretical or flawed.
Oh, absolutely. The practical applications are staggering. Take climate change. AI was just used to redesign the recipe for cement.
Cement, really?
Yeah. Simulated thousands of combinations to find formulations with a dramatically lower carbon footprint. That's huge.
That is huge. What else?
In medicine, again, AI is watching platelets form blood clots in real time, helping spot acute problems much faster.
Wow.
And maybe the most striking one, an AI tool specifically trained on evidence-based medicine. It actually outperformed most human doctors and other AIs on the U.S. medical licensing exam.
Performed doctors.
On the exams, yes.
Correct.
Grounded in evidence. You have this immense capability right alongside the critical vulnerabilities. It's complex.
And it's not just silicon chips anymore, right?
Yeah.
I saw something about light-based AI.
That too. European teams using intense laser pulses through ultra-thin glass fibers, performing AI-like computations thousands of times faster than electronics. The hardware itself is evolving.
Okay, so from quantum weirdness to AI's paradoxical brain, let's move to the physical world. Robots.
Right. Where all this digital and quantum power starts to, well, move around and interact with things.
And they're not just stuck on assembly lines anymore, are they?
Yeah.
They're getting agile, responsive. I even saw the term self-healing.
Yeah, that's the big shift, I think. From rigid, pre-programmed machines to ones that are highly adaptive, almost organic in a way.
Okay, organic is a strong word. What do you mean? Tell me about this self-healing thing first.
Get this. Scientists designed swarms of microscopic robots. tiny things.
Microscopic swarms.
Yeah, and they communicate using sound waves, coordinating their actions like bees or ants.
Yeah.
These little machines, they can adapt to their surroundings, they can self-organize, and if the swarm gets damaged, they can reform, heal the group structure.
Tiny talking robots that fix themselves, that is straight out of science fiction.
It really is. Imagine using them for exploring hazardous places, or maybe even targeted drug delivery inside the body someday.
Wild. And what about bigger robots? Are they getting these more organic abilities too, like senses?
Definitely. There's a huge push for human-like sensing and resilience, like that new robotic skin.
Robotic skin?
Yeah, made from this flexible, low-cost gel. It lets the robot feel heat, pressure, even simulated pain, brings them much closer to a human sense of touch.
Why pain? Why would a robot need to feel pain?
To react, right, to pull back from something damaging, just like we do. It's about self-preservation, operating safely in unpredictable places.
Okay, that makes sense. And self-healing muscles too.
Yep. Another team developed a material for robot muscles that can detect if it's been punctured or squashed too hard, and then actually heal itself, repair the damage.
So robots that can feel their environment and fix themselves when they get hurt.
Exactly. It just opens up entirely new possibilities for where and how we can use them. Think disaster relief, exploration, places too dangerous for people.
That really does change how we'd interact with them, doesn't it? More resilient, more autonomous, more integrated into our actual physical world.
Totally. And they're getting better at navigating that world, too.
How so?
Well, there's this framework called wild fusion. It combines vision, vibration sensors, touch, letting robots sense and navigate complex outdoor terrain, almost like we do.
Vibration and touch, not just cameras.
Right. And then you have things like that robot bird, flies at 45 miles per hour through forests.
In a forest, with trees everywhere.
Yep. With no GPS and no light sometimes, just navigating on the fly in unknown territory, incredible agility.
That's amazing. And I saw something about a robot that transforms.
Oh yeah, the real-life transformer. Morphs in midair. Switches from flying like a drone to rolling on the ground. Seamless transitions.
Okay, the physical capabilities are clearly leaping forward. What about their social side? Are they getting better with people?
That's another big area. There's inspiration coming from, believe it or not, therapy animals.
Therapy horses, I read.
Exactly, leading to social robots that aren't just passive tools but active partners. They're being designed to respond appropriately to human emotions.
And helping people physically, too.
Yes, that elder care robot helps people sit down, stand up.
And catches them if they fall.
Catches them if they fall. That's a huge potential application for assistive technology.
So it's not just about physical tasks anymore. It's about collaboration, assistance, even companionship, maybe?
Potentially, yes. These machines are becoming less like tools and more like, well, collaborators, caregivers, partners in various ways.
Okay, so we've got incredibly powerful quantum computers on the horizon, AI that's learning meaning but still makes ethical blunders, and robots that feel, heal, and navigate like never before.
Quite the picture.
It really is. Which leads, naturally, to the big question, what does all this actually mean?